In the early months of 1945, near the shores of Japan, an American F4U Corsair was forced to crash into the sea after its engine failed during a combat mission. The pilot escaped just as the aircraft plunged into the cold Pacific waters. Not long after, Japanese patrol vessels arrived at the scene, closing in on the stranded wreck. What they pulled from the ocean would soon turn into one of the most valuable sources of intelligence during the closing stage of the war. For almost 3 years, Japanese aviators had clashed with this American fighter across multiple battlegrounds above the Solomon Islands, over Rabaul, throughout the Philippines, and now directly against Japan's homeland defenses. During those years, they had come to recognize the Corsair's blistering speed, its devastating armament, and its rugged, almost unbreakable structure. However, they had never had the opportunity to study a complete, undamaged aircraft up close. Now, for the first time, they had access to a fully recoverable example, something they could inspect, measure, test, and use to determine how far American aviation technology had advanced beyond their own. This discovery was far more than the capture of a single plane. It marked a turning point in Japan's understanding of modern aerospace development. It became the moment when Japanese engineers and aviation researchers finally confronted the overwhelming industrial and technological lead held by the United States. By examining this fighter in detail, they uncovered vital revelations about precision manufacturing, advanced materials, and design strategies that shattered long-held beliefs about their own production capabilities. The Corsair taken from the Pacific was not just another crashed aircraft, it represented the peak of American fighter innovation, a symbol of industrial power that Japan had underestimated until that very moment. Created in 1938 to satisfy strict requirements set by the United States Navy, the F4U eventually transformed from an experimental aircraft into one of the most respected fighters of World War II. Its unique bent gull-shaped wings, gigantic Pratt & Whitney or 2800 double wasp engine, and groundbreaking performance made it a machine that could not be mistaken for anything else. More critically, it accomplished a combination that Japanese designers continually struggled to achieve, an ideal mix of speed, heavy armament, long operational range, and exceptional durability. The origins of the Corsair began in 1938 when the Navy's Bureau of Aeronautics called for a fighter capable of surpassing 400 miles per hour in straight and level flight. This demand alone was extraordinary, as most fighters of that era barely exceeded 350 miles per hour. The Navy's goal wasn't just raw speed, they sought a complete and capable warplane. It had to slow down safely enough for carrier landings, fly up to 1,000 miles, deliver powerful weapons, and even support bomb loads. The idea proposed by Chancelot was bold and unconventional. Lead engineer Rex Beisel, along with his development team, chose to design their fighter around the most powerful engine they could obtain, the Pratt & Whitney R2800 Double Wasp. This 18-cylinder, two-row radial powerhouse was capable of generating 2,000 horsepower, giving the aircraft astonishing potential from the very beginning. This engine output was nearly twice as powerful as most fighters of its era. To put such immense power to use, the designers equipped the aircraft with an enormous 13-foot 4-inch propeller, the largest ever used on a fighter at the time. This instantly presented a major engineering obstacle. How could they provide enough clearance between the propeller and the ground while still keeping the landing gear practical for carrier use? The answer resulted in the Corsair's iconic profile. Instead of building straight wings like conventional aircraft, Beisel's engineering team developed a unique inverted gull shape. The wings sloped downward from the fuselage and then extended outward, forming a noticeable M shape when seen from the front. This design allowed the landing gear to remain relatively short while still giving the enormous propeller the space it needed. Additionally, the downward wing angle where it connected to the fuselage helped optimize airflow, reducing drag and improving performance. The prototype, designated XF4U-1, first took to the air on May 29, 1940, with Lyman Bullard Jr., Vaught's chief test pilot, at the controls. The flight began at the company's airfield in Stratford, Connecticut. Later that year, on October 1, 1940, during a performance test between Stratford and Hartford, the XF4U-1 recorded a ground speed of 405 miles per hour with help from tailwinds. This achievement received national attention, as it marked the first time a single-engine U.S. fighter had surpassed the 400 miles per hour barrier. Its true top speed in level flight was measured at 378 miles per hour at an altitude of 23,500 feet, still an extraordinary accomplishment for an aircraft developed in 1940. Mass production of the F4U-1 Corsair began delivering combat-capable aircraft in late 1942. The first unit equipped for war, Marine Fighter Squadron VMF-124, received its aircraft and deployed to Henderson Field on Guadalcanal on February 12, 1943. The aircraft's introduction to battle was far from impressive. Just 2 days after arrival, on February 14, 1943, the Corsair's first major encounter turned into a disaster remembered as the St. Valentine's Day Massacre. During this mission, American forces suffered heavy losses. 9 aircraft were destroyed, including 2 Corsairs, along with several P-38 Lightnings, P-40 Warhawks, and bombers. In contrast, Japanese forces lost only 1 0 fighter. The staggering 9-to-1 loss ratio so favored the defenders that daytime attacks on Bougainville were immediately halted while commanders reconsidered their strategy. This defeat demonstrated a crucial reality: having a technologically superior aircraft did not automatically ensure success in combat. Pilot skill, effective tactics, and correct employment of aircraft strengths were just as critical. U.S. aviators quickly adapted. They discovered that the Corsair performed best not in tight-turn dogfights but in fast, energy-based attacks known as boom and zoom. Although the Corsair could not outmaneuver a Zero at slow speeds, it could easily outrun, outclimb, and outdive any Japanese fighter. Proper tactics required American pilots to maintain altitude and speed, dive aggressively on enemy aircraft, attack, and then escape before opponents could retaliate. Second Lieutenant Kenneth F. Walsh of VMF 124 became the first pilot to earn ace status in the Corsair on May 13, 1943. He mastered these tactics and would eventually score a total of 21 aerial victories. As 1943 and 1944 unfolded, the F4U Corsair's reputation soared. Marine squadrons operating in the Solomon Islands, taking off from hastily built coral airstrips, exploited the aircraft's remarkable durability to devastating effect. The Corsair could withstand battle damage that would have destroyed lighter Japanese fighters. Its armament was formidable: 6.50 caliber Browning machine guns, with the 4 inboard guns carrying 400 rounds each and the 2 outboard guns carrying 375 rounds each, totaling 2,350 rounds, provided overwhelming firepower. Later models, such as the F4U-1C, replaced the machine guns with 420mm cannons, though many pilots continued to favor the .50 caliber guns for their reliability and ammunition capacity. The Corsair's versatility extended beyond air-to-air combat. By mid-1944, these fighters frequently carried external ordnance, including 1,000-pound bombs mounted on centerline and wing racks, 8 5-inch high-velocity aircraft rockets, or napalm canisters. This fighter-bomber capability made the Corsair indispensable for close air support during amphibious assaults. During the Okinawa campaign in 1945, Corsairs flew thousands of ground attack missions, earning them the nickname Angels of Okinawa from grateful infantry units. Combat encounters, however, only revealed part of the Corsair's story. From the cockpit of a Zero or other Japanese fighter, pilots could see an opponent that was faster, stronger, and more resilient. Fully understanding the engineering and manufacturing methods behind these advantages required hands-on examination of the aircraft itself. Japan's capacity for such technical evaluation was concentrated in 2 main facilities: the Yokosuka Naval Air Technical Arsenal, south of Tokyo, and the Army Aviation Technical Research Institute at Tachikawa. Throughout the war, these organizations had studied captured Allied aircraft, recovering examples from Pacific battlefields. Their work provided useful intelligence about American technology, but most captured planes were damaged or incomplete wrecks salvaged from crash sites. An intact, operational frontline fighter like the Corsair represented an extraordinary opportunity. The Yokosuka facility had been conducting technical research since April 1, 1932, when it was reorganized as the Kaigun Kakusho Naval Air Arsenal. By World War II, Yokosuka employed thousands of engineers, designers, and technicians. The arsenal had designed numerous Japanese naval aircraft, though production was contracted to manufacturers such as Aichi, Nakajima, and Mitsubishi. Yokosuka's engineers were highly skilled professionals with deep knowledge of aircraft design. When a salvaged Corsair arrived at Yokosuka in early 1945, it represented one of the most modern American fighters yet recovered in relatively intact condition. Although the aircraft had suffered water damage during its forced landing, the primary structure remained solid. Recovery teams had taken care to prevent it from sinking completely, and the plane was transported to Yokosuka's secure technical area for detailed examination. The initial assessment focused on the aircraft's overall condition. Despite having been submerged in salt water, a large portion of the Corsair remained in recoverable condition. The powerful Pratt & Whitney engine would require complete disassembly and extensive cleaning, but the airframe itself showed no signs of battle damage. This detail was extremely important. Previous attempts to study captured Allied aircraft were hindered by the fact that most examples were severely damaged, making it hard to separate actual engineering design from destruction caused by combat. Japanese analysts began their study with meticulous measurements and detailed photography. Every component was documented. They recorded a wingspan measuring 40 feet 11.7 inches, a length of 33 feet 4 inches, and a height of 15 feet with the wings unfolded or 16 feet 2.3 inches when folded for aircraft carrier storage. The inverted gull-wing construction drew immediate interest. Although Japanese engineers understood the aerodynamic and structural advantages of the design, they also recognized the enormous manufacturing difficulty behind it. Creating the complex curves and maintaining exact wing angles required precision tools and strict quality control that Japanese factories, by this late stage of the war, could not consistently perform. During the inspection, one finding in particular surprised the research team. Despite being a highly advanced fighter, the Corsair did not use metal skin on every surface. Large sections of the outer wings, specifically behind the main spar and gun bays, were covered in fabric instead of metal. The same was true for all control surfaces, including the ailerons, elevators, and rudder. At first, Japanese aviation experts found this curious. By 1944 and 1945, nearly all modern fighter aircraft were built with fully metal outer skins. Closer examination revealed a far more sophisticated truth. The use of fabric was not a sign of shortcuts or outdated engineering but an intentional design decision dating back to the Corsair's development phase between 1938 and 1940. It reduced weight in areas where structural forces were low, conserving aluminum for sections that required maximum strength. The material used was specially treated fabric that, when applied correctly, provided ample durability, weather resistance, and strength, while being noticeably lighter than metal covering. This reflected an advanced understanding of how to distribute resources intelligently for the best performance outcome. Once the wing was taken apart, the construction methods left the technical staff both impressed and uneasy. The primary wing spar, the most critical structure supporting flight loads, was an enormous forged piece of extraordinary quality. American metallurgical processes had produced aluminum alloy forgings with strength levels that Japanese industry found extremely difficult to replicate. The spar's strength and size surpassed anything found in Japanese fighters of similar class. This component alone highlighted a crucial distinction: American factories could manufacture large, complicated forged parts with reliable uniformity, whereas Japanese production increasingly depended on building structural pieces from many smaller segments. The rest of the wing's internal framework revealed comparable sophistication. The ribs, which were stamped out of aluminum sheet, displayed exceptional accuracy and uniformity. Each rib matched the next almost perfectly, revealing manufacturing processes governed by tightly controlled precision standards. As the war continued, Japanese aircraft production increasingly faced problems with consistency, with individual planes showing significant variations in component quality. Examiners then focused on the Corsair's weapons systems. 6 Browning and /M2.50 caliber machine guns embedded in the wings delivered formidable firepower. The installation was compact, dependable, and designed for straightforward maintenance. What impressed Japanese evaluators was not just the raw firepower, but the comprehensive design of the system. Ammunition boxes, feeding mechanisms, spent cartridge ejection, and charging systems were all engineered to operate together flawlessly. The guns themselves were examples of highly precise manufacturing. American ordnance production had achieved levels of reliability that Japanese industry could only envy. The Browning M2 machine gun was a mature, time-tested design perfected over decades and produced in the millions with remarkable uniformity. Japanese technicians examining these weapons recognized production methods and quality standards that their own factories could not consistently meet. The presence of 150 pounds of armor plating protecting the cockpit and a 1.5-inch thick bullet-resistant glass panel behind the windscreen further reinforced the philosophy behind American aircraft design. Japanese fighters had generally sacrificed heavy armor for reduced weight and improved maneuverability. The early success of the Zero seemed to confirm this approach. However, as American fighters became faster, more powerful, and better armed, the lack of protection proved deadly. The Corsair demonstrated that with proper engineering, substantial armor could be incorporated without compromising performance, made possible by the enormous output of the Pratt & Whitney R2800 engine. The engine quickly became the centerpiece of the technical investigation. The Pratt & Whitney R2800 double wasp exemplified the pinnacle of American aircraft engine development. With 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches and producing over 2,000 horsepower, it was a true mechanical marvel. This power plant represented a masterpiece of engineering. Japanese technicians had encountered the R2800 in captured aircraft before, but they had never had the opportunity to study a unit in such relatively intact condition for detailed examination. The engine's construction revealed manufacturing capabilities that seemed almost beyond comprehension. Each cylinder was machined with tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshaft components exhibited surface finishes and dimensional precision that Japanese engine makers struggled to replicate. Its two-stage supercharger, designed to maintain power at high altitudes, featured complex internal passages and precisely fitted rotating components. Comparable Japanese supercharger systems had largely failed due to manufacturing limitations. Arguably the most remarkable aspects were the engine's reliability and sustained power output. American radial engines routinely delivered their rated horsepower for hundreds of operational hours between overhauls. Japanese engines, even brand-new examples, often fell short of theoretical ratings and required frequent maintenance. The R2800's consistent performance was the result of superior metallurgy, advanced lubricants, highly precise manufacturing, and sophisticated quality control measures. The aircraft's propeller system proved equally informative in illustrating the extent of American engineering expertise. The Hamilton Standard hydraulic propeller, measuring 13 feet 4 inches in diameter and featuring variable pitch functionality, demonstrated advanced aerodynamic engineering and sophisticated hydraulic control systems. Japanese engineers were familiar with propeller theory, but they lacked manufacturing capabilities to produce such large propellers with the precision required. A detailed examination of the Corsair systems revealed consistent patterns of superior design and execution. The landing gear assembly was intricate yet manufactured with exacting precision. The cockpit instrument panel contained an extensive array of gauges and controls, surpassing anything found in contemporary Japanese fighters. The fuel system incorporated self-sealing tanks composed of multiple layers of specialized rubber compounds that expanded when punctured, effectively preventing catastrophic fuel loss, technology largely absent in Japanese aircraft. The electrical system efficiently powered numerous components using high-quality wiring, carefully insulated and well-organized. Perhaps the most striking observation was the overall quality of materials and workmanship. Every part, from major structural members to small fasteners, demonstrated consistent excellence. Aluminum alloys displayed uniform properties, steels were correctly heat-treated, and surface finishes were smooth and professional. The aircraft exuded a sense of durability and robustness, built to endure extensive operational use. This level of quality starkly contrasted with Japanese aircraft production in 1945. Wartime shortages forced widespread use of substitute materials, aluminum quality declined, skilled labor had been drafted, and factories operated under constant threat from American air raids. Production schedules prioritized quantity over quality, undermining craftsmanship. The examination of the captured Corsair took place at a moment when Japan was facing imminent defeat, highlighting the technological and manufacturing gap between the two nations. American B-29 bombers were methodically leveling Japanese cities. The Imperial Navy had been crushed at Leyte Gulf. The Philippines had been retaken by U.S. forces. Iwo Jima had been captured, and Okinawa was being attacked. Within this dire situation, the examination of the Corsair held a grim meaning. It was no longer an attempt to gather intelligence for future battlefield success, but rather a final confrontation with the truth of technological disparity. Engineers at Yokosuka and Tatsukawa produced technical reports explaining their observations. These documents recorded precise measurements, described production methods, and evaluated America's industrial capabilities. Although written in a professional tone, they could not conceal the underlying message. In almost every field of analysis, American engineering surpassed what Japan could achieve. The technological divide was vast, not something that could be closed quickly or easily. It reflected decades of industrial progress, enormous financial investment in research and machinery, advanced production logistics, and abundant resources, advantages Japan simply lacked. By the time the war concluded in August 1945, at least 2 Corsair aircraft had fallen into Japanese hands. Evidence indicates that engineers attempted repairs on at least one, bringing it near flying condition, as photographs show captured Corsairs with visibly patched fuselage panels and wing surfaces. Whether the Japanese ever succeeded in conducting actual flight tests remains unknown. However, the attempts to restore the aircraft make it clear that they had genuine intentions to operate it for thorough testing. When American forces occupied the Yokosuka Naval Air Technical Arsenal in September 1945, they discovered substantial proof of extensive Japanese technical research on the captured aircraft. Various captured Allied aircraft were positioned throughout the facility. Technical documents, diagrams, and photographs recorded Japan's efforts to analyze and comprehend Allied engineering. American intelligence personnel gathered these records, understanding that they held significant value in revealing what Japan had discovered. The account of Japan's detailed study of the F4U Corsair is not only a case of technological investigation, it also represents the enormous divide between American and Japanese aviation by the end of the war. When the Corsair first saw combat in early 1943, Japanese pilots flying Zero fighters could still hold their own by relying on superior flying tactics and exceptional pilot skill. However, by 1945, even seasoned Japanese aviators flying newer designs had almost no realistic chance against a properly operated Corsair. The aircraft's technological edge, paired with the overwhelming numerical dominance of U.S. forces and superior American pilot training, created a hopeless disadvantage for Japan. The Corsair achieved an officially recorded kill ratio of 11-1 against Japanese aircraft. American pilots flying the Corsair shot down 2,140 Japanese aircraft while only 189 Corsairs were lost in combat during World War II. These statistics demonstrated far more than the Corsair's advanced engineering, they revealed the entire advantage of America's war effort. It wasn't just a superior aircraft. The United States possessed better trained pilots, far stronger logistical systems, enormous production capability, and cutting-edge technology in every category. Japanese engineers who inspected the captured Corsair recognized all of this. They could quantify the performance differences, study the manufacturing contrast, and clearly see the massive imbalance in resources. The technical reports they produced ultimately served as an admission that Japan could not compete with America's industrial power. The Corsair itself continued its career well beyond World War II. It served again in the Korean War from 1950 to 1953, proving highly effective in ground attack and close support missions even as jet fighters replaced propeller aircraft in air-to-air combat roles. Several foreign militaries, such as France, continued to operate the Corsair in various post-war conflicts into the 1960s. The final combat use of the Corsair took place in July 1969 during the brief soccer war between Honduras and El Salvador. On July 17, 1969, Honduran pilot Captain Fernando Soto, flying an F4U-5, shot down 3 Salvadoran aircraft. This included 2 FG-1D Corsairs, marking the final combat victories ever achieved by the aircraft type, ironically earned by shooting down other Corsairs. From its initial flight in 1940 to its last operational missions nearly 3 decades later, the Corsair stood out as one of the most durable and successful fighter designs in aviation history. For Japan, the discovery and study of the Corsair represented only a portion of a much broader confrontation with the realities of advanced technology during the years of American occupation. Japanese scientists and engineers, who had struggled throughout the war with limited resources and constrained industrial capacities, now worked alongside American occupation administrators to rebuild Japan's industrial foundation. The insights gained from studying American engineering, including the Corsair, influenced how Japan approached manufacturing in the post-war period. The modern Japanese focus on precision, high-quality production, and continuous improvement can be traced back to the difficult lessons learned when Japanese engineers observed what U.S. industry was capable of producing. The Corsair, recovered in early 1945, symbolized more than just a downed aircraft. It represented a tangible demonstration of engineering mastery and manufacturing skill, qualities that Japan had long attempted to match but had been unable to attain during wartime. Although the information gained from it came too late to alter the outcome of the conflict, those lessons helped shape the nation's future. By studying this American fighter, Japanese engineers came face to face with the true scale of the technological challenge their country had faced. They had fought bravely and skillfully, yet bravery and skill alone could not defeat the enormous technological and industrial superiority possessed by their enemy. The conclusion of this story is not one of celebration, but of recognition. The Japanese technical documents detailing the Corsair, later discovered by American occupation personnel and now preserved in archives, stand as quiet evidence of a moment when one nation's engineers were forced to confront the capabilities of another. The Corsair they studied no longer exists, most likely dismantled or melted down during the turbulent years after the war. Yet its impact endures through the knowledge it provided, demonstrating what advanced engineering could accomplish when supported by ample resources, proper planning, and sophisticated production methods. Japan's aviation industry would eventually return after the war, rising anew in a completely different era. However, its designers and engineers would never again underestimate what American industry could produce when backed by vast manufacturing power, scientific expertise, and the means to bring ambitious concepts to full reality. The 1945 investigation of the F4U Corsair by Japanese specialists marked a turning point, an instant when the nation's aviation leaders finally understood the enormous technological divide that had formed during the conflict. It was a revelation conveyed not through propaganda or battlefield claims, but through aluminum structures, precision metalwork, and carefully engineered tolerances that revealed more than any written statement ever could about the true strength of American industrial might.